Welcome back. We're ready for graphs of logarithmic functions. So we're going to graph each of these logarithmic functions by plotting points. So remember, if we write that as log base 2 of x equals y, using our swirly-do definition, that's the same thing as saying 2 to the exponent of y will equal x. If we're to do an xy table and plot points, it may be more helpful to actually put in values of y first instead of x. So we can go from -2 all the way to 2 with our integers and plug it in. So 2 to the -2 would give us an x value of 1/4. 2 to the -1 gives us an x value of 1/2. 2 to the 0 is 1. 2 to the 1 is 2. And 2 squared gives us 4. So let's plot each of those points. When x is a positive 1/4, y is a -2. When x is a 1/2, y is a -1. X is 1, y is 0. When x is 2, y is 1. And when x is 4, y is 2. So we have a nice increasing function. Notice there, no matter how close to -infinity we get for y, we're still going to get a positive reciprocal. So our graph is not crossing that y-axis. Now let's look at the function g of x equals log base 1/2 of x. If we rewrite that, log base 1/2 of x equals y. And again, think of it in terms as our swirly-do definition. That would give us 1/2 to the power of y equals x. So if we plug into an xy table to come up with points, again, we'll probably want to plug in for our exponent or y value first. So we'll use y values of -2, -1, 0, 1, and 2. 1/2 to the -2, you take the reciprocal and square it, we would get a positive 4. 1/2 to the -1 gives us a positive 2. 1/2 to the 0 power is 1. 1/2 to the first power is 1/2, and 1/2 squared is 1/4. Let's plot these points. When x is 4, y is -2. When x is 2, y is -1. X is 1, y is 0. And x is 1/2, y is 1. When x is 1/4, y is 2. So we have a decreasing function. And again, notice how close to -infinity our y becomes. Our x just approaches infinity, but it never becomes 0 or negative. It never crosses the y-axis. So let's take a look at some of the characteristics of these graphs of a parent logarithmic function. In other words, f of x equals log of some arbitrary base b of x. Remember, b cannot be negative or 0. And x has to be larger than 0, in other words, positive, and b cannot equal 1. Is it a function? Yes, it passes the vertical line test. 1-to-1 function? Yes, it also passes a horizontal line test. So that means we can find an inverse. Horizontal asymptote, there doesn't seem to be a value that the y is approaching when the x gets large, either positively or negatively. There are no horizontal asymptotes. However, there are vertical asymptotes. Notice we're not shifting left and right. It is not crossing the y-axis. So that's a vertical asymptote of x equals 0. The domain, notice it's only starting right after 0. So our domain goes from 0 to infinity to the right. Our range, however, covers everything top to bottom. So we go from -infinity to infinity. Our x-intercept is at 1, 0, whether it's increasing or decreasing. Since it's not crossing the y-axis, then there is no y-intercept. It is increasing in that first graph from 0 to infinity, but notice in that first graph, our base was greater than 1. In the second graph, it's decreasing, still from 0 to infinity, but in that one, our base was between 0 and 1. There are no local maximums or local minimums. It is completely increasing or decreasing over the entire function. Same thing as global. There are no endpoints to check. So in number 9, it's talking about the end behavior if b is larger than 1. So we're looking at the graph on the left, part A. If it's greater than 1, the end behavior as x is approaching positive infinity, our f of x is approaching infinity. Now it's slower, it's not like an exponential, but it is still creeping upwards. Local behavior means we're not approaching negative infinity, but something's happening as x is approaching, in our case here, as x is going towards 0. So as x approaches 0, and I would even say 0 with a little plus sign up there, that means it's approaching 0 from the right-hand side. Our function value is approaching negative infinity. It's going downwards. Number 10 talks about our base being between 0 and 1. And what's happening there as x is approaching infinity to the right, f of x is approaching negative infinity. It's decreasing slowly, but it is decreasing. Local behavior, so as x is going in the other direction, never quite heads towards negative infinity. It stopped there at 0. So as x is approaching 0, our function value is going upwards towards infinity. In example 2, they've asked us to find the domain of this logarithmic function below and express it in interval notation. Remember, when we have any log base b of its argument equals y, we know the base has to be positive and it can't be 1, which means our argument also has to be positive. Well, in this case, our argument is not just x, our argument is a linear expression. So that still holds. 7 minus 2x has to be positive because 5 to any exponent will give us a positive number. So we can solve for this inequality. We can subtract 7 from both sides. And remember, when we divide both sides by a negative, we have to switch our inequality sign. So we have an x less than 3.5. So if we write that in interval notation, x is everybody to the left of 3.5. So that is negative infinity all the way to 3.5, 3.5 not included. If you're still struggling with interval notation, draw the number line, put in your 3.5. We know it's not included. X is everybody to the left, which means it's going towards negative infinity. And remember, our interval notation is always written from left to right, smallest to largest. So that's why it's negative infinity first, 3.5 next. So that guy is our domain.